Well, hello everyone, and welcome to lecture 12, where we continue to look at scattering techniques for the characterization of colloidal aggregates or surfaces. So the next technique that I want to consider is neutron reflectometry, a very, very important technique whenever you need to probe the structure of a surface of a material. So what is the general principle behind neutron reflectometry? Well, what we do is we irradiate an interface with a highly collimated beam of neutrons. So again, you see that term collimation. We're using a very well-defined narrow beam of neutrons, and we irradiate a surface with that beam of neutrons. And we do that at very, very shallow angles relative to the surface. And neutrons are then reflected by various interfaces within the sample, and we can record them on a detector, and it can tell us something about the surface chemistry, namely the structure and composition of the surface, but some other interesting parameters can be pulled out of the data. Now, the intensity of that reflected wave is dependent on the refractive index profile across the interface. And if we analyze the neutrons that reflect as a function of the angle of incidence, that grazing angle of incidence, we can tell information about the surface, and we can get down to sub-angstrom level resolution here. So again, a very, very sensitive and powerful technique. So within neutron reflectometry then, our angle of the incident beam is equal to the angle of the reflected beam, and we describe that momentum transfer vector Q that we spoke about in the SANS lectures as a normal perpendicular to the interface, and that describes the change in momentum of a neutron after it is reflected from the interface. So when a neutron passes through an interface, its direction will change due to a difference in refractive index across the interface. And Snell's law relates the refractive index change across an interface to the angle of incidence and the angle of refraction. So there, theta I is the angle of incidence and theta refracted is the angle of refraction. Due to the physics of the system, if we irradiate a surface at very, very low angles, and due to the way in which neutrons interact with matter, the angle of refraction is equal to 0 if we're at very, very low angles, and we get a situation called total external reflection. So every neutron that hits that surface is reflected, and this is known as the critical angle. If the angle of incidence is equal to the critical angle, then this total external reflection occurs. And if the angle of incidence is greater than the critical angle, then neutrons penetrate the sample by refraction and are also reflected from interfaces. What it means then is that at angles above the critical angle, you can irradiate your surface with neutrons, and the neutrons penetrate the layers of the sample, and they are reflected from each interface within a sample. And those reflected neutrons can constructively and destructively interfere with one another. Now, that constructive and destructive interference creates a series of maxima and minima as a function of the angle of incidence, and that can tell you something about the surface. It tells you the thickness of each of those layers within your sample, and how quickly the reflectivity falls off as a function of incident angle tells you something about the surface roughness. So, Again, with this technique, we've got to model the data. So we can't just take the data from the instrument and have these parameters. We have to model the data here. So we model a mathematical fit against the experimental data. But once we've modeled the data, there's lots of information available. We can learn something about the density of the interface, so the surface coverage. So think how important that is if you're trying to accurately determine the critical micelle concentration, for example. Very important for looking at lipid layers as well. We can work out the roughness of an interface, and we can work out the thickness of the surface layers. And we can determine those things to within a few angstroms, if not sub-angstrom resolution. So we can work out the thickness of a single layer of molecules on the surface of water, for example. And we can even differentiate between the head group and the tail group of a surfactant. And again, we can use contrast variation, just like we can in small angle neutron scattering. Now, one of the questions is when you think about using neutrons, then some people might ask, well, why can't you use X-rays? And you can use X-rays for both small angle scattering and reflectometry. The mathematical principles are exactly the same, but X-rays interact with the electron cloud of atoms and neutrons interact with the nucleus. So there's a summary here of the disadvantages and the advantages of using X-rays and neutrons, and use the rest of this time, the rest of this lecture, to think about those. So to kind of summarize, I've given you sort of three little mini lectures, three little mini videos, along with some reading. Scattering techniques are very, very powerful. Now, I don't want you to remember all of the equations that I've shown you. I just need you to be able to describe the techniques and understand which one is appropriate. And I'd also like you to have a solid idea of the advantages and disadvantages of using neutrons versus X-rays.